Partial differential equations. Partial differential equations. All right, let's do some math. So just in case you missed the announcement, we're looking at partial differential equations today. I hope that was clear. And what partial differential equations are, they are equations where partial derivatives and derivatives of our function with respect to multiple different variables are actually how we define the function. It is known in terms of its rates of change with respect to each of the different component variables that goes into it. Like, for example, we might have a relationship between the spatial derivatives of a function and the temporal, the time derivatives of that same function, where the rate of change in space influences the rate of change in time. And we have to have a toolkit for dealing with that. Before we get into the tools, I want to talk about how these things are written. So the reminder from the previous lecture is that we have this subscript notation for indicating partial derivatives. So f sub x instead of df dx, and f sub t instead of df dt. And you can certainly use that notation. It's great. I like to use it quite a lot. There's a second set of notations that I think you see this more in physics textbooks rather than math necessarily, but you'll see prime for spatial derivatives and dot for temporal derivatives. And I think I probably shouldn't say this out loud because it's probably going to be wrong, but I feel like that actually goes back to maybe Newton and like his notation for derivatives of things. I need to look that stuff up. Ignore everything I said for the last 30 seconds. Onward. It's not actually entirely true that I only know one way to solve PDEs. I actually know like 3 or 4, but there is one favorite that I highly recommend it so much that it's mandatory in this class. Hooray. And that is separation of variables. It is our good friend returning again. You can definitely solve some partial differential equations with separation of variables. And so that's what I'm going to teach in this video, is how to do separation for PDEs and not just ODEs, ordinary differential equations, which are single variable. Now, the reason that I bring this up is that it is useful in material science specifically. I'll look at an application at the end of the video, but lots of physically important problems, you can write this function, this overall function of spatial and time variables as a product of functions of the individual variables. And this is the idea of separation, is that we were going to solve for each of these ones individually and then build the total solution by multiplying all of those functions together at the end. That's the goal. In order to get there, we need to start by taking our partial differential equation and trying the separation process. So there's an algorithm for this. I'll show it to you. Not all equations are separable. Some are just not. So the first thing that you do is test, does this work? And once you have those functions separated, so you have starting from one PDE, turn it into multiple ODEs that are decoupled from each other, then you can solve each of those using whatever tools you have in your toolbox. Now, in general, in this class, this is going to be the only analytical approach that we really spend a lot of time on. I will mention 1 or 2 others later in the semester, but the emphasis in this class is going to be on numerical solutions, on using computers to find numerical answers to partial differential equations. And there's a couple reasons for that. But the biggest reason is simply that that's how it's done. In the modern working world, the problems that people are solving, for the most part, do not have analytical solutions. They're simply too complicated to have exact answers that you can write down in terms of elementary functions. So this is a very practical necessity. Having said that, doing some practice with problems that are analytically solvable helps you build your toolkit, learn these tips and tricks, and get a more intuitive sense for what you expect the solutions of complicated problems to look like and feel like based on your exact solutions to simpler problems. So we're going to start with that. And to teach separation of variables, I'm just going to work out an example start to finish, and we'll go through this step by step, and that will illustrate how the process works. So we have a function, u. It's not me, it's you. This is all about you. The class is for you. We have u of x and y. So two input variables here. And the partial differential equation is this one. Remember, ux means du dx. So y squared times the x derivative of the function minus x squared times the y derivative of the function equals 0. So y and x are our input variables, and u is the function that we're trying to find. You are the function that we're trying to find? That sounds great. Okay. Step one for separation is assume that separation works. Now, we will test this assumption. We'll find out whether it works or not, but that is the starting point. And then what you do is you plug this short solution into your full PDE and then, go through it after you collect yourself and get ready to do some math. After you do some math at the end of the day, hopefully an answer comes out. If an answer does not come out, it does not necessarily mean that you made a mistake. It may mean that the equation is not separable. So just to be aware of that. If I give you a problem in this class and I'm like, solve this by separation of variables, it will be solvable with separation of variables. But one way that you can know a problem is not separable is to try this and have it blow up in your face. All right. So here's our worked example. Basically the rest of the video is just going to be going through this one. So we start by plugging in the assumed separated solution that u of x and y can be written as f of only x times g of only y. So our mission is to find the f and the g functions that make this work. So we plug them in. You apply your partial derivatives. The x partial derivative acts only on the function f because g is not a function of x. And then likewise, the y partial derivative acts on only g because f is not a function of y. So that's why we have just plain old g hanging out here and just plain old f hanging out there. The derivative has ignored them because of which variable we're differentiating with respect to. Now, I did not mention this in the partial derivatives video, but when you have a single variable function and you take a partial derivative with respect to its one variable, that is the same thing as a regular derivative, just plain old df dx, no curly d's. So the next thing that I'm going to do is to take this form and write it in terms of just the regular single variable derivatives. This is starting to look like something that can be separated. Like, oh, it's all multiplication and division. Oh, the other thing I did was to take this entire thing and move it over to the right-hand side of the equation, just add it over to the right. So this looks good for separation because you say, oh, I can multiply and divide and I can get my f's on one side and my x's on that side, and I can get my g's and my y's on the other side, and this is good. So that's exactly what we need to do some multiplying and dividing, and now this is separated. You can see all of the y stuff is on the left, all of the x stuff is on the right. It's a bad expression, but it is separated. This gives us hope. Now, this is the big logical leap. This is the clever step that you have to do for separation of variables to work. Looking at that expression that we had on the previous slide, I'll actually just bring it back up here for a minute. So look at this. We have this crazy function of y in terms of y and the function of y and the derivative of that function, and like all of that business is somehow equal to a function of x. X and y are two different variables. They're independent of each other. So you should be like, how is it possible for these two things to be equal when x can change and when y can change? You could imagine them being equal at one point, like there's some place where those two functions cross each other. But how could they always be equal to each other? And the answer is, it is only possible if they are constants. If that function is actually a constant function, In that case, you can have one constant equal to another constant if they are the same number. So you're like, so we're just solving for constants? Well, let's see where this goes. Because it's not that the total function u is a constant, it's that the function is going to be a product of two expressions, and some version of those expressions can be written in terms of a constant. Again, the logic here can seem a little convoluted, so if you just need to like stop and ponder it for a minute, that's totally fine. But what we're saying is that this expression on the left in terms of y, in order for it to always equal that expression in terms of x on the right, the only way for that to be possible is if they are constant and equal. Now we can separate the variables one at a time, because now we have that this expression in terms of x is a constant. And so you can do separation of variables like we did with ODEs earlier. Get your f's on one side, get your x's on the other side, do your multiplication and division. Now this c, this has a name. This is the constant of separation. It is not, in my understanding, it is not a constant of integration. We didn't integrate anything to get c. We discovered c as a part of the process of separating the y and x variables from each other. So we have this constant of separation in the problem, and that will be ultimately tied to the boundary conditions. So in order to get a specific solution, we'll have to figure out c at some point. But for now, we can just leave it in as an unknown parameter. It is great to separate. It is also really great to integrate. That's why great is in integrate. I bet you didn't know that one. That's not true. All right. So we integrate and integrate x squared on the left. That's easy. You know how to do that. And then a reminder, I saw a lot of mistakes on this on the last quiz. Careful with your constants of integration when you have 1 over something as your integrand. Because when you integrate that and you have logarithms in there, you need to remember your properties of logarithms. Like the sum of two logs is the log of the products of the arguments, that kind of stuff. You do need to be careful about those things because it can actually change the answer if you forget about those properties and do those wrong. Okay, so we're going to integrate 1 over f and get log of f, and we are going to integrate x squared and get 1/3 x cubed. Ta-da! So now we have these new constants of integration, d and e. Do a little bit of collecting of terms. This entire thing, this is a constant. D is constant, C is constant, E is constant. So that combination of them also has to be constant. I point this out because just to make the bookkeeping a little nicer, just so there's not as much visual clutter, we're going to start collecting terms and collecting like terms. So to get to the solution, we have done separation of variables, we got our constant of separation, and then we solved this x equation by separating and then doing some integration, and we're almost there. We're almost ready to write f of x. So I divided my c over to the left-hand side, and now I'm going to exponentiate after redefining my constants here. Because, so this 1 over c and this 1 over 3, I'm just going to smush those together and call that a. So a is just a constant that happens to be equal to 1 over 3c. And then this b, that is the collection of all of these terms. So I'm just giving it a new name just so the equation looks nicer. I mean, you can see the second line is simpler to write than the first line, but it contains all the same information. Okay, so now I take my exponential, e to the ax cubed plus b, and then finally, I am going to do one last repackaging because, again, properties of exponentials, property of logarithms. This is e to the a x cubed times e to the b. And since e to the b is a constant, I'm just going to write it in a slightly simpler form and just call it big F. So this will be the coefficient that I get from the initial values in the problem. And hooray, we did it. Actually, we solved for f of x. This is f of x. To get values for big A and big F, those will come from the boundary conditions in a specific problem. But this is the general solution. So now you could, of course, continue and find the function of y. In this particular problem, I chose a problem that would be really nice to get started with. You're going to get the same thing because they actually were the same equation. The y and the x equation were identical, just with different variables. But more, more broadly speaking, you'll have to solve for your x function and then also solve for your y function, and then finally your total answer, the u of x and y, is going to be the product of those individual separated functions. Okay, we already had singing today, so I won't do the Linkin Park joke, but anyway. All right, so we get this, we find f of x, we find g of y, we multiply those things together, and then that is the total function. As with all differential equations, you can check your work because once you find what you think is the answer, you can plug it back into the original equation. And if it satisfies the original equation and everything balances out, then you know you did it right. So that's how we do this thing. Why does it matter? Well, I'm so glad you asked. Because the thing is, there is a problem in material science that we really care about. And it's part of our overlap with chemistry. There are these things that materials are built out of, these constituent parts. I don't know if you've heard of them. And in order to understand the chemical properties of atoms, we need to be able to describe how their electrons behave. What is the orbital structure? Because the orbital structure determines the bonding properties, and bonding properties determine properties of matter. So it really all comes down to, what do the electrons do in the atom? And you've seen, hopefully, pictures like this in your chemistry classes where we have these wonderful three-dimensional visualizations of the electron orbitals around atoms. And so we have our s orbitals that are spherically symmetric, and then we have our p orbitals that have the sort of dumbbell shape, and then we have the d orbitals that have the crazy shapes, and the f orbitals that have the really crazy shapes. Don't even get me started on g orbitals. So like, if you haven't seen these things, first, by the way, this is what orbitals look like. But where do these things come from? How do we create these pictures? And don't say in Photoshop, that's not what I mean. What I mean is, how do we solve the equations that tell us where the electrons live around the atom? This technique of separation of variables in partial differential equations, that's how we find these things. So what you have to do is you have to say, okay, here's my problem. I have a nucleus at the center of the atom, and I have an electron out here, and there is going to be some distance between them, r, yes, like r for radius, but also this is a three-dimensional problem. Like you see your Bohr atom in your chemistry textbook and the electrons are going in little circles. Like atoms are not two-dimensional. They're in our physical three-dimensional, four-dimensional universe. Time is a dimension. That's where I was going with that. So, we've got X, Y, Z, T, and all these things interact with each other. We have, you'll see it in another 2 weeks, the partial differential equation that tells you how the electron orbits the atom. And it has space derivatives and time derivatives in it. And it has this interaction that depends on the distance between the nucleus and the electron. And when you put all those terms together, you get a separable partial differential equation where you can write the radial function times the angular function. So what we end up with is this thing where it's like the wave function of the electron is going to be some radial function, some function that only depends on distance. This is where we get our energy levels from. There's a little more to it than that, but like this really is a key part. At different radii, we get different distances where the electron orbit. You can see this really nicely in the s orbitals. Like you have these different regions. Here's one region, here's this middle region, here's this third region. Those are places where the probability density of the electron is high, which you get as high points in this R of R equation, where at certain distances the electron is more concentrated. So those are um, where our orbitals come from as a function of distance. But you can see angularly these things have shapes too. Not the s orbital. The s orbital is spherically symmetric, but in general, for all of the other orbitals, you're going to have an angular function, something that depends on your spherical coordinate angle, so your polar angle and your azimuthal angle. And this is what gives us the shapes of all those lobes in the p and d and f and g orbitals, is this angular function that comes from separating the variables in Schrodinger's equation. Solve Schrodinger's equation in the presence of an electrical potential from the nucleus of the atom. These are the solutions that come out, and they're solutions of a radial function, which depends on your energy level, times an angular function, which depends on the angular momentum of the atom, and that's your P's and D's and F's and so on. So maybe we'll get into some details with that later this semester. I hope we get there. But if nothing else, I wanted you to hear the story of where these come from. This is a great application of separation of variables to material science. So I hope you liked it. And with that, we're going to wrap this up. 20 minutes. This is the only required video for today. If you've heard of partial differential equations before and you feel okay with this, you're good. If you just want a little more detail, a little more context, there will be a second optional video for today where I just get into a little bit more of the description and justification for why we do these kinds of things. So check out that second video if you're interested, and then either way, I'll see you in class.